Well, hello everyone. Thank you so much for joining us for today's LJC event with Michael. You may remember his previous talk, so I'm really excited to have you back. We're really glad to hear from you again. For those of you who don't know me, let me introduce myself. I'm Abby. I work with the LJC and the other communities that are run by RecWorks. They're all run completely free for our members, so you don't have to pay anything unless it's a particular event like a conference. But other than that, all our events are free for our members. So who are RecWorks? Well, we are a tech recruitment company, but with a huge difference. So obviously, as a company, we're always on the lookout for more clients, and some of our best clients have actually come from community members who recommended RecWorks to their internal talent teams. So if you are hiring for a new team or you're working for a company that is, we would love to hear from you. If you want to know more about what we can offer, just ping me a message on Slack or LinkedIn. My name is as you see it on the screen. Sorry, and we really look forward to working with you. So what's the difference? Well, also as a company, we really do believe that recruitment can be a force for good in the industry beyond just placing people in jobs. We have a particular focus on learning, mentoring, and personal development, and that is where our communities and events come into play. If people want to learn and others want to teach or share their knowledge, we are more than happy to connect you through our communities and events. We see this as giving back to those we've worked with in the past, but also paying it forward to those we hope to work with in the future. To date, we have run hundreds of events for engineers and developers, students, graduates, CTOs, the list goes on. We've run conferences, lightning talks, hackathons, all sorts. Earlier this year, we actually made 5,000 introductions through our Meet a Mentor program. We're really excited about that. Again, it's another of our free communities, and we're really looking forward to making our 6,000th introduction through that group. As I've already said, we love to give opportunities for people to connect, and this event is part of that. If you want to know more about any of the other communities we run, again, please just get in touch with me on LinkedIn or Slack, and I can take it from there. The recording of today's session will be available for you on YouTube. I will put the link to the channel in the chat. If you have any questions while Michael is speaking, he has said if they're short questions, we can ask them immediately while he's talking. If it's a longer or more technical, in-depth question, please wait till the end. There will be time to ask more detailed questions later. So without further ado, I would love to just hand over to Michael for Peril Streams. Oh, you mean parallel streams. Over to you.
Yeah, I always like the title with the confusion, and it sometimes makes it more attractive to talk about such a topic. This is the second talk I now give about Peril Streams, but I still have a small poll. Can you just put into the chat which Java version you're using at the moment? No numbers yet. Never mind. Then let's first say some words. Okay, Java 8. My first talk was about sequential streams, and the main reason was for that parallel streams are very complicated to use, in my opinion, and that's why I thought at that time I make a separate talk out of it, because it's plenty of material. And that is this talk now. It is very difficult, by the way, to find good examples for parallel streams, because nearly all are quite exotic, if they are somehow useful at all. And it took me some time to get good examples. Just a small note. I'm used to give short times where I'm silent, where you can read the slide, think about what I told you, and understand what I said. So from time to time, I will be silent, but I'm not dead. So don't be afraid. You showed me now which Java versions you use. I see many 8s. Nice. I don't see any 6 or 7. then I would be really very afraid. Can you just enter with Y and N for no, whether you have watched my first talk? It was Java Streams, or you mean Java Streams, Java Streams for the advanced? Okay, well, no. Okay, never mind, it's not a problem, because we really, when you look on parallel streams, it's not necessary that you have watched the first one. Okay, who of you has used a parallel stream already at Office or in his private projects? Just a Y or a no, N for no? Yeah, it is recorded, Roberto. So no, okay. That's not surprising me, because parallel streams, as I said, it's quite exotic, and also the examples are quite exotic, and that's why my experience is that you don't use them very often. Okay, and last question. Oh, yeah, nobody has used one parallel stream, then I should not ask whether it was faster or not. Okay, let's start. First, I will introduce myself for those who don't know me yet, and I want to show you when parallel streams are useful, so some general rules. Then I will just show you how parallel streams work basically, and then I will give you some advice how you can make a sequential stream expression better, so that the parallel stream benefits from that. Because with sequential streams, it's not very difficult. I mean, sequential streams nearly always work quite good if you don't do stupid things, but the parallel streams are very special, you will see. I will give you some examples for that. And then there's also the problem with parallel streams. When things are parallelized, then there will be a lot of garbage sometimes. And I want to show you an example and show you how you can fix such issues. I also want to show you an alternative solution, a fork join pool solution, and warn you of some effects or things that you have to keep in mind whenever you parallelize, and especially with parallel streams. Okay, who am I? I'm 38 years old in Munich, Germany, Oktoberfest. I guess everybody knows it. I work for the Yambit GmbH in Munich. And I really like to work for them. They're really great. I studied computer science 10 years ago. I graduated. I have 18 years experience of Java, 10 years of working experience in full-time, mainly Java or nearly all Java. I had the chance to contribute to JMH and JC Stress, two very wonderful and useful tools by Alexei Shipilev. And I gave them some samples that he accepted and put into his repository. I've got some GitHub projects where I try to make it easier for other people to understand some features or to understand how to apply some patterns and principles, but it's at the moment at the start. And also I'm a very enthusiastic improvisation theater player for the last 13 years. And I love it. And I also have two cute nieces. And you can find me on GitHub, on Twitter, and soon on Mastodon as well. Okay, first I need to start some things in general. I know that it's always tempting to increase the performance and to optimize everything. But sometimes that can be a very bad idea. That's why I would like to remind you that in projects, not in private projects, but in commercial projects, you should always insist on a concrete requirement and only optimize if if the performance is not good enough and you need more performance. And it should really be a concrete requirement, not just like it must scale or it must fast. That's not something you can measure. Otherwise, you will never know how much you optimize and for what. Second, you should only really optimize stream expressions, sequential ones, if you really notice that they are the bottleneck. If they aren't, don't touch them. That's at least my advice for you. And last but not least, there are, of course, many other ways to parallelize solutions. The question, of course, is why should you use a parallel stream for parallelism? And I think the main reason here applies as well to sequential streams. It's that you have a high level of abstraction with streams. And the very nice thing on parallel streams is that you don't need to give it up. However, parallel streams are only sometimes useful. I hope at the end of this presentation or talk, you will somehow be able to guess whether a parallel stream could be useful or not. Okay. First of all, in 90% of all situations, I noticed that parallel streams always make only sense if you have a lot of data. And most of the time, at least for me, you don't have so much data, so that it doesn't make sense at all to think about parallelizing it because it's so small. And you have to always keep in mind, of course, that parallelism always introduces some overhead. And this overhead can be quite high, and especially with parallel streams. And as a rule of thumb, I would say that you should have at least 1 million or 10 million ints, for example, in an array. Of course, it also depends on this the question what kind of operations you do, but I will come to it. Also, it's very, very important, but very overlooked that all the data you have, you must be able to easily and in a balanced way to split them up into pieces. And a very good example where it actually doesn't work at all is linked list. And good examples are usually arrays. They are quite easy to split, and you will see more about that. Of course, which is also very important, it must really be, the data must be independent from each other. If you have some concurrent hash maps and other things for caching and so on with locks, then this can really decrease the performance of your parallel stream tremendously. And that's why that's very important. Also, you should always keep in mind that those operations that run in parallel, they really must do a lot. If they only do summing 10 integers, the overhead is extremely huge. And there are, by the way, the expression embarrassing parallel problems. Who of you has heard about that? Sorry, Abby, you are raising your hand.
I'm so sorry to interrupt, but I feel like you're saying things and your screen should be your slide should be changing, but it isn't. We're still on slide 1, so I didn't know if we're meant to have seen things as you've been talking. I've been very intrigued.
That's confusing. One moment, I share once again. One moment.
Yeah, it looks like a couple of the guys can't see your screen either. So it might be worth stop sharing and then start and reshare, and hopefully we'll catch up with you.
One moment, I'm sorry, I'm really confused why that happened.
Yeah, no, me too.
Can you now see your screen? Okay, that's the first slide.
Yeah, I can see your first slide.
If I now click here to the next slide, can you see something other?
No.
Hell, what is the hell? What's going on here? That's confusing.
Because it usually works absolutely fine, doesn't it?
Yeah, I'm really surprised. I have never had that situation where it didn't work. That's strange. One moment.
That's okay. We can edit this bit out while we're working it out. It's okay. I need to improvise one moment. Yeah, no worries.
You know, the problem is that my slides are always shown on the third screen, and now I have to somehow cheat with my PC that it doesn't matter anymore. Just a moment.
Yeah, no worries.
You know, this was the wrong thing. I've got an idea. I will just take away one monitor and force them to use other monitors. Okay, I switched away the third monitor, so it can't use it. Can use it anymore.
I think a couple of us were having problems with it for some reason. It was very strange.
Okay.
Doesn't normally happen like that, does it? But
no. Just let's have a next try. Sorry.
Yeah, no worries.
Okay, I took away the third monitor, and now I should be able. Can you now see something?
Yep, can see your first slide.
And now the other slide?
Yeah.
That's strange. The weirdest thing I have ever experienced so far.
Yeah, I'm so sorry. I didn't, like I say, I didn't want to interrupt you, but I think
no.
It obviously got stuck somewhere in the process, and I didn't want anyone to miss what we need to be seeing, obviously.
No, you are completely right. I mean, you can't follow me if you can't read my slides. Okay. Sorry. One moment. Okay. Here we were, and that was before what I told you about myself, but it's not so important. You can read it later once again. The first things I said to you was about that with the optimization, only optimize if you must. And the other things that I wanted to say here was that you need to keep in mind you must have a lot of data. You must be able to split it in a balanced and easy way. Otherwise, it won't work. You need to really be able to process the data independent from each other. The more caching and dependencies you have, the less your performance will become with the Peril stream as a rule of thumb. Also, you should have at least 10,000 CPU cycle operations. You really need to do something with the data. And here, my last question was for you. Who of you has ever heard about the embarrassing parallel problems yet? Can you just give me a hint in the chat and with Y and N, just tell me if you have heard that expression and maybe even know what it means? For those who don't know it, okay, I see I know, it means that there are some, let's say, trivial operations like in math that adding to numbers or multiplying to numbers if they're small is so little effort for our CPUs that it doesn't make sense, for example, summing 1 million ints in an int array, because you will rather measure the access time of the memory than actually the time of the operations, because those operations are much too small. And that is meant with embarrassing parallel, where you always have to be careful that it might be, in the end, not measuring what you want, but something other. Okay. Also, very important here, if you need to merge your results, for example, creating a new list and copying from other two lists and do all the time, so many memory operations, then you will also get problems with the performance. And you also have to be careful with the memory. I guess most of you all know that memory is quite slow compared to CPU operations. And I will later show you an example where you can really see how the access time to the memory lacks all the performance. Also, you should keep in mind that if the order of the data that you process is relevant, and you need to do it in a special order, then also that decreases the performance because you force the order, and that costs performance. Also keep in mind that stream expressions may not create too much garbage, because you can imagine that if you parallelize something that causes a lot of garbage, it will cause much more garbage when the parallelization is enabled. And this can also destroy your performance. And last but not least, very important, the parallel stream at the moment is really optimized for CPU-intensive tasks. So if you are, for example, indexing your hard disk or all the files, or do other I/O stuff, or for a server or something like that, parallel streams will yet not be very useful for you, because you will have very I/O-intensive tasks. And I know that, well, I'm pretty sure that with Project Loom, with the virtual threads that are now introduced into Java, there are some plans, so far as I know, to support I/O-intensive tasks with virtual threads in parallel streams in future. But I think it will take some time before this really has happened. Okay. That's one of the moments where I want to give you some time to think about.
Sorry, Michael, is your slide meant to have changed again?
Okay. No, I haven't changed yet.
No.
You're on mute, sorry. You're on mute by accident.
That's fine. I just wanted to check that we hadn't...
No.
No, lovely.
Now you see arrows? Okay, wonderful. Okay, what you really need to know about parallel stream is that they have a kind of structure. And the structure of the parallel stream is usually that at the beginning you have a split iterator, and split iterator is somehow a splitting iterator from the word here, And the idea is that you can implement a splitting strategy by giving a split iterator, and usually what it does is to somehow halve the data into pieces, and usually the number of logical cores minus ones. For example, when your CPU has 4 cores with hyper-threading 8 minus 1, then you will have 7 threads in fork join pool, if I'm not wrong. And then the split iterator will split it into 7 pieces and then give it to those fork join pool threads, and they will run through it and create results, which are then merged. And in the second phase, with the process data, there actually happen all the intermediate operations. And in the end, in the last phase, all those results are merged together with the last operation, which is usually the terminal operation. Okay, don't be shocked if I use some mathematical things here, because they have the advantage that you cannot calculate or evaluate things in your head. So you need to try out some things like that. Who of you has ever heard of the Collatz sequence in math? It's no shame if you don't know it. I have known it. I hadn't known it 3 years ago. But then I noticed it, and it's quite interesting. Okay, in the next examples, I will use that Collatz sequence. And if you look on here on the first 4 lines, you first see 2 examples, and then 2 more or less general examples in line 3 and 4, and then some code below. And just read it and try to understand it. It's, I hope, not too complicated. who thinks he or she has understood how the Collins sequence works? Just a yes or no into the chat. Okay, for those who had some problems to understand what's going on here, in the line 14 to 17, you see that if you have an even number, then you just divide it by 2. If it is an odd number, you do 3 times it plus 1, and then it can become will become an even number. And you just do it as long as possible, and you will always end up in the sequence in line 1 at the end, 4, 2, 1. And mathematicians have tried to understand and to prove whether this always happens and why it happens. Nobody was so far successful, and I think it's a problem from 1934. And the bottom line here is you need to try out to find out how many steps it takes. There are some formulas which converge faster, but there is not a kind of Gauss sum formula where you can directly calculate that. And the useful thing here is also that from one number to another, there can be a huge difference of, let's say, 100 steps between, and you cannot predict it in advance without trying it out. And that's why it's very useful for the examples I will show you. You cannot just take a piece of paper and a calculator to calculate it without trying it out. Okay, we will see in the next example why it is so interesting. Here, have a look on this code here, and I will tell you why that is so interesting. And on the bottom, you see, by the way, JMH benchmark. May I ask who of you knows JMH or has used it? The micro benchmark harness by Alexei Shipilev. It's no shame if you haven't used it yet. Good. So what you see here is that between lines 1 and 7, you see an example with iterate and limit. And you can write such an expression. And if it is sequential, the performance will be the same. However, if you want to use a parallel stream, then iterate and limit make it harder for the parallel stream to parallelize all the things here, because it's not clear from the beginning which numbers will come from that infinite stream that is limited by that intermediate operation in line 3. And that makes it very difficult for the parallel stream to optimize it very well. However, if you use in line 9 just range closed, then the parallel stream knows from the beginning that it has a kind of array with 10 million entries in it, and it can really directly split it in a balanced and easy way. And that's why, as you see on the bottom, that range closed parallel stream is about 3 times faster here than the first stream. And as I said, with sequential streams, it doesn't matter. With parallel stream, it matters a lot. Yeah, now somebody might say, well, and if I don't go in steps of 1, if I go in steps of 3, for example, or what if I do need to have it in a descending order and not in an ascending order? Well, there is a trick. Have a look here. I'm sorry that there are some German words in that slide. I will fix it later. Okay, I hope everybody noticed that the trick here in line 2 and line 7 is that we just map the numbers we need. And we can, of course, map the integer in line 1 to 3 multiples of 3, but just multiplying it with 3. And also we can do the descending order with map as well. And I would do it in that way, and it is quite fast, I can tell you so far. So you really don't need iterate and limit in these cases. Okay, as I said before, sometimes order can cost performance. Have a look on this example here. Oops, sorry. Okay, what you should see here is that we want here a number where you need 400 colored steps before you come to the 1. And if you don't need the first solution, but just one solution, it is, of course, better for the parallel stream, because it can split up the data and then just look for a number and just pick out one of them and not the first one. Because here in the first example, it really needs to always check whether it is the first number it found with that property. And the second example, it doesn't matter. And if you don't need the order here, just use find any in this case here. And you see it is definitely faster or below about 3 times here. So use it if you can. Okay, now it gets a bit more difficult. When you use reductions, then reductions often somehow use immutable data, and then this can cause to a lot of garbage. In this example here in line 1 and 2, you should see that this is a task, an exercise from Advents of Code. I think it was called a chemical reduction. And it's a very simple problem that you somehow replace a capital letter and lowercase letter, as you see in example 2. And this is a solution you can do with sequential streams, but you will get a lot of problems with parallel streams. Have a look on here and try to understand the code. Good. I hope you noticed in line 4 to 6 that we just have to somehow cast the characters, because unfortunately the .chars delivers us not characters but ints. That's why we need line 5 here. And in line 6, you see that typical reduction, that you have a first element from which you start. Then you have a kind of reduction method that here they reduce. That always somehow calculates the next value from the existing result and from the new letter. And last but not least, you just combine all those intermediate results. Here, as it is a sequential stream, this combine method will not be used, because combine is only used when you do things in parallel and have results you need to merge. In line 9, you see that we just either remove the last letter in line 10 with the first code here, or we just append it at the end of line 10, depending on whether we have found such a pattern or not. And last but not least, we just use the left side and then do the reduction for everything on the right side and combine this. I hope that's not so difficult for you. However, if you do this with a long string in parallel, it won't work probably, or will be extremely slow. You can fix that problem in a quite easy way, but you have to be careful. This would be, for example, a solution that uses the mutable string builder and somehow can avoid all those copy and new strings which are created on the fly. Just have a look and try to understand that code here. I hope it's not so difficult. Okay, I hope you noticed that we don't use any reduce here anymore. And the simple reason for that is that with the collect, we can collect the results in parallel. And then we can just use something like a string builder, which is not thread safe, because we don't need to care. If there was a reduce here in line 3, we would get a lot of array index out of bounds exceptions and many other things, because this one string builder would be used by all parallel streams, by all parallel threads at the same time, and that cannot work. So it's important to use here collect and also give a factory method for a mutable data structure. And as you see here on line 4, instead of creating new strings where we either remove the last character or just add the new character, we somehow manipulate the string builder. And this, of course, avoids copies we don't need to. And the only things we need for that is delete and append here. And this example here, by the way, in line 6, you could just call parallel, and it would be probably faster. But the interesting thing here is with that mutable approach that even if you don't parallelize it, it will be very fast. So there's a question how much faster you need it and when you need to call parallel here. And if you wonder how much the effect is, and here are some numbers. The 4 first numbers here, they give you the time, how long it took in line 1 and 3 for a string of 200,000 characters. And you see the GC alloc, that means how much memory is consumed. And you can see that it is a huge effect. It is 500 times faster from the time. And if you look on the memory, it's also a huge difference. And what's also interesting is that that if you use that string builder with 20,000 and 20 million characters here, it's still very fast. So you can parallelize it, but in many cases you must not parallelize it, maybe, because it is already fast. Okay, now it gets a bit more complicated. Look at this innocent stream expression. I have shown that one expert on Twitter, and he was so nice to tell me, Michael, don't do that. you're not sure what you're doing here, I guess. And then he explained me some very, very interesting and useful insights and explanations. And I've learned a lot from this example here. But give it a try. I guess everybody of you know factorial for math, that you just multiply the factors going down by a step of 1. And of course, you know that there are huge integers, the result, and that's why we here need big integers. But just give it a moment and try to understand what's the problem here in this example. Or try to find the line, which line creates the problem. It's not line 3 only. Okay, I want to point out that this traffic sign, be careful. I really put it there because stream expressions like this can really look completely innocent. But now I give you the solution. Well, first of all, let's see what's good in this expression and then see what's bad in that expression. But first of all, the result of this will be correct because big integer is thread safe. And the way we do here, calculating the factorial, works. Also, this expression is quite short. And also, it will be faster than the sequential version. And I think that's unfortunately completely undervalued often. Expressions like this would not be the final solution, but just an intermediate solution, which helps you to find the final solution, for example, by comparing the results or to compare the performance. Because if you want to have a faster solution, then you need to compare it with something. And that might be a good start because that's the most primitive way to calculate the factorial with a parallel stream. So it might be a good start. But the main problem here is that, first of all, as I told you before, it's not splitted so much. I mean, we have here 100,000 factors. And if I tell you that you might just split it into 7 pieces, then this is not really much parallelization, actually. And also, it's not only split it too few times, it's also underused the parallelism that's possible here. But which is even worse is that big integers use the Karatsuba and the Tom Cook multiplications for very large big integers. And I can tell you so far that those very efficient ways to multiply numbers are hardly used at all. I will show you later numbers where you can see that it does not really benefit from that at all. So you might now ask, how could it be better? And I want to first show you a solution with the fork join pool, which is quite easy to understand if you have understood the principle, which you can often use, but you somehow need to remember the pattern, which is nearly always the same. Just a short question. Who of you has used the fork join pool directly, also not indirectly by a parallel stream or by something other? So who of you has written code like this that you see here on that slide? Just a small yes or no answer in the chat. It's no shame if you haven't used it yet. Okay, interesting. Somebody has used it, others not. For those who have not seen something like this here, the pattern is that nearly always that you have like with recursion, and it is in the end recursion, a criteria when you stop in line 8. And then you just split the data in line 10 and 14. Just read it. I hope it's not too complicated. Okay, for those who don't know this pattern, in line 10 to 14, we usually split by half, because then we get a binary tree and little recursion only, but splitting extremely. As you know that you have the powers of 2, and you also have only the depth of the binary logarithm. And splitting by half is a very efficient strategy. This one is here used. However, you have to be very careful with the fork and the compute here. If you call it in the wrong order, then you won't have a parallel solution. But apart from that, I think it's quite easy to understand. And you know, the most awesome thing on that, I must confess that I've tried several weeks to beat that solution here, to find a faster solution, and I was not able. I did all kind of optimizations. This solution always seemed to be the fastest one, although it doesn't matter about big integer here. I will show you some numbers later to show you how good this solution is. But I must confess, I was thinking like, well, the Peril stream must also be an option. We have to optimize it a bit. And before you read this code here, which might be a bit difficult for you, let me sketch what actually happens here. In line 7, you see that at the end of the line, the usual way to calculate factorial is n times n minus 1 times n minus 2 times in this order here. Unfortunately, if you do it that way, you will have the fewest number of Karatsuba and Tom Cook multiplication. So this is the most inefficient way, actually. And that's why what you actually can do is to group the factors. And you can see that in the middle of line 7, that you, for example, have the group from n to n minus b, and then some groups between there, and then a last group n minus c times until 1 down. And if you do it that way, it has the same result from the value here, but it makes a huge difference considering the performance. Because if you do it that way, you will get very fast, very large numbers that use the Karatsuba and Tom Cook multiplication. And in line 12, you can't know it, there's a threshold because the multiplication is only efficient with big numbers. And I mean, 2,560 bits is very much for a number. It's about, I think, a 1 with about 800 zeros behind it. And with Tom Cook, it's about 3 times of it. And the basic idea in line 3 that you can see here is that we somehow multiply all the things so as long as possible, and first start to multiply the huge numbers when they're huge enough for Karatsuba and Tom Cook. And that's why we have that array in line 3, where we somehow order the multiplications. Okay, and just have a look for the rest. I hope you might understand what happens here, because it is very clever, and it took me some time to really get the idea here for that. It's not trivial. Okay, for those who have still some problems, maybe some further remarks. In line 8 with the accumulate method, what happens here is in line 9 that we first start to multiply it with the smallest product that we have here. And if we then notice that on the right of the array, we have a number which is big enough for Karatsuba multiplication, we just multiply it with the other Karatsuba product we already have. And we do the same for Tom Cook as well. And that maximizes the number of Karatsuba and Tom Cook multiplications we use here. In the end, of course, we have to merge all those three products by just multiplying them together, because in the end, we will not just have a Tom Cook product and the other products. What I mean is there will be remainders of the numbers. And in line 14 to 16, we're just somehow multiplying everything together and returning it. And that's the solution so far. It is quite tricky, okay? If you now wonder how much the effect is, if you just consider that factorial of 100,000, you can find out that there are at most 591 Karatsuba multiplications possible and only 196 possible. If you look to factorial parallel stream, it performs very bad. It only uses 63. So it's about only 10% of all Karatsuba multiplications possible and only 30% of Tom Cook. And if you compare that with the forked joint pool, the effect is tremendous. You see that forked joint pool, even as it doesn't know anything about big integer, it uses 488, that is 83% Karatsuba multiplication. And also it uses with 126 multiplications in line 3 with 64%. It is quite efficient. I was really surprised. However, as you know, or as I told you, I wanted to see whether I can optimize it. And what I noticed and that was very interesting, that I was able to optimize the parallel stream to perform better. But I've completely failed to optimize the forked joint pool solution by increasing the number of Karatsuba and Tom Cook multiplication that you will see on the next slide with the results. So those are the benchmark results that I got. Have a look on that and try to find out where there might be some surprises. Maybe I forgot to say something. If you wonder what this parallel multiply and sequential multiply means in the end of the name, thanks to Heinz Kaputz, we have a parallel multiply method for big integer with Java 19, and it can improve the performance tremendously as well. So thanks to him, we have that method. And here I just used it for those who use Java 19. And for those who don't use Java 19, they only have sequential multiply. So what's interesting here on that slide with the numbers? Well, I hope you first noticed that the winner of this benchmark is the forked joint pool solution with the parallel multiply. It really beats all the others. What's also interesting is that the parallel stream here is even 2 times slower than the forked joint pool solution. as you see here, if you compare line 1 and 3, and if you compare line 2 with 4. However, if you look on line 5 and 6 and line 7 and 8, you will notice that this Tom Cook-Karatsuba multiplications optimizations have a good effect actually. Oh, I'm sorry, I meant line 7 and 8. You notice that if you compare them with the others, then you notice that the parallel stream gets quite fast, or is nearly as fast as in line 1 with the Fock-Joint-Pool solution. However, if you look in line 5 and 6, you will notice that trying to optimize the number of Tom Cook-Karatsuba multiplications makes the Fock-Joint-Pool slower and not faster. And the main reason for that is that there is a collision between splitting as most possible and collecting as many multiplications as possible to get high numbers that can use the Karatsuba and the Tom Cook multiplications. And that was very surprising for me. However, you might now ask the question, which solution shall I use? And for what is the parallel stream then useful in this example? That's a difficult question. I mean, if it's all about performance, of course, you would use that Fock-Joint-Pool solution with the parallel multiply. However, if performance is not the only option or the only feature in your decision, then there might be something interesting here for you. I mean, if I go back here to that solution, well, in line 2 at the end, you see that dot parallel. Well, if you remove that dot parallel, then you will have the most efficient sequential solution so far, considering that optimization, because you will get as most Tom Cook and as most Karatsuba multiplications which are possible. And now you might wonder, for what is that useful? Well, if you not think of slow latency, so fast results, but of little effort, high throughput, you will have here an expression that where you get high throughput if you leave out the dot parallel, and you get a low latency if you put there the is parallel, and it's only the parallel, and that's the only difference. So you can switch between them. Unfortunately, you cannot really do that with the Fock-Joint-Pool solution, but the Fock-Joint-Pool solution was for parallelizing and not having options for sequential solutions. However, of course, this accumulate method and this combine method here, you can use it with a for loop as well. You don't need to use a stream. So you would have an alternative for the Fock-Joint-Pool solution without streams. Okay. Now, here is a very, I would not say popular, but very mean pitfall. And the sad thing is that I've seen in official presentations, I don't want to say any names here, where people multiply, not multiply, sum the numbers from 1 to n and do it in parallel. And then are proud that the parallel stream is faster summing them than sequential. Can somebody of you tell me in the chat in few words, what's the most efficient way to sum the numbers from 1 to n? I'm pretty sure somebody of you knows it. So what's the most efficient way to sum the numbers between 1 and n? Okay, for those who might, because it's so late at evening, yes, the sum formula, right, the Gauss sum formula. So n times n plus 1 divided by 2. And you know, that's the worst example that I've seen. Really using a parallel stream to sum from 1 to n. Also, you can do it with the Gauss sum formula. Stupid, I'm sorry to say that. But this problem here is to avoid this mistake, as you see here, I use really random ints. And if the ints are random, you cannot just sum it by the Gauss sum formula. You really need to sum them. And there are many ways you can do it. And here I just have several solutions. And most important is the first one uses an array, an int array. The other one uses an array list. And the last one uses also an array list, but the values were sorted. And that has a tremendous effect. The effect is this here. Have a look on that and find out what's quite interesting on those numbers. Okay, I hope everybody noticed that this int array is the fastest solution, no matter whether we use it in parallel or just in sequential. The array list, the unsorted one, is much slower. And if you sort that array list, then it gets even worse. And the reason for that is, first, as I told you before, summing is an embarrassing parallel operation. It's extremely fast. So the CPU mostly waits for the numbers to sum than just summing them. And the problem here is the memory layout. I guess most of you have guessed it. The int array has the advantage that it's really a block in the memory where there are one number after another, directly neighbors. On the right, as you see here. On the left, with the boxed integers, the numbers are actually spread over the heap. And you just have many references within that heap. And if you sort them, you confuse those pointers, and what you get in the end is cache misses. So the CPU is waiting all the time for the numbers to add. And you might wonder, what's the solution? Well, if you have a fixed number of integers, you can use, of course, the int array. However, if the int array has a size that you don't know in advance, well, then sometimes it might be a good idea to use Apache Commons, Java, or Eclipse collections where you have support for integers in lists, which use an int array below and not an object array as the array list from the Java collection framework. And by the way, if you compare that int array with the integer list of Eclipse collections, for example, you get the same results, which is not a surprise. And you need really to keep that in mind here, that the memory is slow, and if you do only little operations, that you can run into that pitfall. Okay, some of you might think, well, what can be the result when you parallelize something? Well, the first result is that it's slower than the other expression that doesn't use a parallel stream. The second thing, but what could happen is also it hangs up. I've seen that as well, but which is even worse, and that's what I wanted to show you here. We can get an out of memory exception. And just have a guess. What do you think? Which of the lines 5, 6, 7, 8, or 9 might be the reason for the out of memory here? Or let's say 5, 6, or 7. Which line do you think is the suspect? Just enter a number between 5 and 7. What do you think? Okay, line 7, interesting. Okay, line 6. Now I'm waiting for line 5. Okay, it's indeed line 5. And for those who want to know more about that, there's a Stack Overflow question where I asked the Stack Overflow community what's actually going on here, because I was surprised when I noticed that just by accident. And what I was not really aware of that is that the skip here is a stateful operation. So it needs to memorize which were the first 2 elements to skip them. And as we have here, up to 10 million numbers, that's a huge state it gets, or it needs to memorize. And with parallelizing, it's even worse. And you can fix that issue by using unordered. However, unordered also means that it won't be the first 2 that you skip, but just the first 2 random numbers. And even if you move the skip below the limit, well, then you reduce the number of ints you process. And I hope you remember now what I showed you with the first slides, that if you just use range closed here, you won't run into that problem with the out of memory exception here. The out of memory exception here is a product of the combination of the use of iterate, skip, and limit. That's fatal here. And last but not least, there is a grouping concurrent, but I won't tell you much about that because we are a bit over time now. That's why I want to go to the summary. And what I can recommend you is to keep in mind that you really need to think about before you parallelize a stream, and should think about whether you have enough data, whether you can split the data, whether the data can be processed independently and the operation do a lot, and also that you don't need to merge a lot of the results in the final result. If you notice that most of the question you can say, no, it's difficult or whatsoever, then most probably you will not benefit from a parallel stream. Also, keep in mind that the split iterator is responsible for the split strategy, but be careful. A split iterator can, as far as I know, offer to split something into 20 pieces. But from what I know so far is that the parallel stream doesn't need to split it into 20 pieces if it's possible. It can only split it in 7 pieces if it wants. So you cannot force the most number of splits, as far as I know. Second, if you see a stream expression and see iterate and limit, keep in mind that for parallel stream, this would be a bad idea. And you usually can use range closed instead of iterate and limit. Then keep in mind that if it is not important which result you get, just one result, and it can every result, then just use find any instead of find first. If you have more than 10,000 groups, if you put them into a map, group them in a map, then it can be helpful. If you have a smaller number of groups, just use grouping by. Keep in mind that if you have a reduce method with an immutable data structure, that you can create a lot of garbage, and that can be very bad for parallel streams. And just look out whether there is a mutable data structure, and then use it maybe with collect together and avoid all that garbage. Then keep in mind that the parallel stream is not the only solution you have. There is also that for joint solution, and as you noticed before, it was relatively easy if you have understood the pattern, how you do it. And that was the biggest surprise for me, it was very efficient, even without knowing what it was actually doing or splitting. And keep in mind that if you call .parallel, it can not only be smaller, it can also hang up or even cause out of memory exceptions. And last but not least, keep in mind that parallel streams nearly always reduce the latency, so you get results faster. But for throughput, they were very bad because you consume much more resources than actually needed. So if you want to have throughput, I think it is a very bad idea to use .parallel, to use a parallel stream. And the last one, I can only say it, if you have a sequential solution which is fast enough, whatever it is, a sequential stream or whatsoever, just use that one. Don't take any risk with parallelism that you don't need. And that's so far everything I can tell you about parallel streams. I hope you have learned something. I hope you have some questions, maybe some feedback, some interesting experiences you made. I would be open. It would be very interesting for me. And thanks for your attention. And thanks, Abby, for inviting me.
Oh, you're welcome. Thank you so much for coming to speak to us again. Does anybody have any questions for Michael? I'm just going to give it a few moments in case anyone's putting anything in the chat. Obviously, that can take a few seconds. So.
And remember, there are no stupid questions, only stupid answers.
Yeah, definitely. I agree.
I hope I did not made everybody feel like, oh, which question could I ask? Hey, thank you so far, Chris.
Oh, there you go. So Roberto says, how do you debug parallel streams?
I know that it sounds like ironic, but it is extremely difficult to debug parallel streams. Theoretically, you can use the peak method that gives you result. But the problem is, first, the results will be in kind of random order. And that will be the first problem you face. And the second, which is even worse, is that in the Java doc comments, you will find a sentence which says, if the peak method you use disturbs parallelizing it, we won't call it. So you cannot rely that peak is called, at least according to the Java doc. My experience so far is it is still called, but whether it's so useful, no. I would say that I have made several experiments with first writing a solution which does not use a parallel stream, but works like a parallel stream somehow, and then to debug that one, and then later translate that into a parallel stream. Because, you know, you can first write a sequential solution and then just imitate a bit the parallelization. And if you just imitate it, but have no parallelization, then you can debug it very well. But of course, it's extra work. But what I noticed, by the way, is that when I wanted to debug the fork join pool solution and put a breakpoint in the compute method, then I noticed that it went once in the breakpoint, although it went into it 20 times. And the other 20 times it didn't went into the breakpoint. And when I then put a system out print line to see the lines printed out, then I noticed IntelliJ in this case ignored the other calls. It only jumped into that one breakpoint. Also, I had a suspend all threads breakpoint. So this didn't really work. And that's why, once again, use a sequential solution if you can, because sequential solutions can be tested very easily. They can usually debugged very easily. You have many dangers with parallelization. And that's why I think it's a risk. You should really think of whether you need to take the risk. And as I showed you before, sometimes you can optimize solutions, sequential solutions, in a way that they get very efficient. And then you sometimes might not use any parallelization anymore because you have an efficient sequential solution. Okay, there was a question here.
I think you kind of just answered it. The question was, you know, whether a parallel solution is better than sequential. So just test both methods and choose the more performant run.
Yeah, I mean, I would be careful. I mean, I would not always sacrifice everything to performance. Performance is a killer argument for even the worst code that you can read, that somebody says, well, it's fast. And that's why I said before on the first slide that you should have concrete performance requirements. And then you can always check, are you fast enough or not? And if you are fast enough, then you don't need to sacrifice, for example, a better readability of the code or simpler code or something. But if you just have no concrete requirement and think I need to optimize it to get into the Guinness Book of Records with my program as being the fastest one, then you will never know whether you have reached your goal, and you will never know what you gave up. And as I showed you before, the Peril Stream is a bit slower, but with only one call on the method, you can switch between two different solutions with two very good use cases. And there are always considerations. I think there is not really always the best solution. There are only trade-offs. So that's why I would always keep in mind that you should not always only think about the computer executing it fast. You should also think about your colleagues, well, how long it takes for them to understand your code. And the irony is nobody measures it and nobody really cares about it. But I think it would be nice in future that it's not about is it 10 milliseconds faster or not, but does it take for a colleague 5 minutes or 30 minutes to understand it? That would be more interesting considering the performance.
So it's getting the balance of everything put together when you, yeah, lovely. Any further questions for Michael? I haven't seen any more come up in the chat so far.
Maybe a last word on benchmarking.
Mm-hmm. Go for it.
I told you before that I use GemH, and the main reason is that the problem with Java is, or I send you a private message, I wanted to send them all. The problem is writing a good benchmark is actually very difficult. And the main reason for that is that first, you may have to make sure that you really measure what you want to measure. And think of that sum example that I showed you before, where you not measure how long it takes summing ints, but how long it takes to transfer the data from the memory into the CPU. The second problem is often to find an area where you can really measure, because if the error gets too high, you can give up your results. However, if the results are too small, you cannot really see a difference between them. So you need somehow to arrange as much data that you get results where you can really find out, had one optimization a good, a bad, or no effect. And that's the second problem that's difficult. And this last one is in Java that the JIT compiler and other things in the Java virtual machine they optimize very aggressively. And the unfortunate part on that is that the results can somehow be random by that optimization. And if you just always get kind of random results, you can never say what was the effect. And that's why you need stable results. But getting stable results which you can compare is also very difficult. And in Java, we are very lucky that somebody like Alexei Shipilev wrote such a tool that somehow some use tricks to avoid the JIT compiler use optimizations that create random results. So JMH helps you to get stable results, but writing the benchmark and make decisions how to measure it, that's what you need to do. And by the way, JMH is not perfect. Alexei Shipilev always says JMH is good, but if you get strange results, JMH can also be the culprit. So writing benchmarks is very difficult. It would be an own topic.
Excellent. Thank you so much, Michael, for coming to speak to us again. Like I say, it's a pleasure to have you, and really great to have some of these really nice in-depth kind of looking into things. So thank you so much. And thank you to everybody who's joined us today and everyone who's watching the recording. I hope you've had a great session and found out some things you maybe didn't know before. I'm sure if you want to know more, Michael will be available and happy to answer questions, so please do get in touch if you want to know anything further at all. He's more than happy to continue the conversation. But yeah, all that's left for me to say is thank you so much, everybody, for joining us. Thank you, Michael, for sharing some more of what you know, and I really look forward to seeing you all at our next LJC event. Thank you so much. Have a great evening. Take care.
Thank you. Bye.
Bye.